The next example is probably going to be the last example in this, well, yeah, in this group I prepared 4 examples. Here we need to evaluate the integral where we have x multiplying a radical. The radicand is x squared plus 2x plus 4. Okay. So in this case, we're going to use a combination of techniques. We're going to start by looking at the trinomial that is the radicand, and we see if we can come up with a binomial. We know how to deal with x squared plus something or something minus x squared. So what we'll do to start with, we complete the square of the radicand. Okay, so we're going to say that x squared plus 2x plus 4 equals to x squared plus 2x plus something such that this will be a square of a binomial. But since we are adding, we need to subtract by the same amount, and then let's add the 4. That was the original number. And what we add and subtract eventually will be 1/2 of the coefficient of x. So 1/2 of 2, of course, is 1, and 1 squared is 1. So we add and subtract 1. And what happened is now we have x squared plus 2x plus 1, which is x plus 1 squared. So this is the where we're going to end up. We're going to end up having this equals to x plus 1 squared. And here we have negative 1 plus 4. Well, that would be 3. Okay, so this is the new radicand. Instead of x squared plus 2x plus 4, we have x plus 1 squared plus 3. And now we are ready to do the first substitution. Because we want something square, that something, we're going to let it be, we call it z. Because I want to reserve u to a later substitution. So let's call z as being x plus 1. And therefore, we have x equals z minus 1, and we need also dx, so the substitution for dx is dz, so that's easy. Okay, dx, we require it because we have x times the radical. So now we can redress our integral. So our integral originally x times the square root of x squared plus 2x plus 4 dx. Now it looks like the integral, instead of x we have z minus 1, and inside the radical we have the quantity z squared plus 3. So let's write one more thing here. X squared plus 1 squared plus 3 equal z squared plus 3. dz. And now we're going to write it as, we're going to break it down into two integrals. The first one will be the integral of z times the square root of z squared plus 3 dz, and the second one will be the integral of the square root of z squared plus 3 dz. And in order to replace it with name, we're going to say this will be equals to the first integral. We call it I1, integral number 1, and the second one will be I2. Okay? Because at this point I'm going to work on I1 separately, and then I'll work on I2 separately. So let's look at the first integral, I1. I1 is the integral of z times the square root of z squared plus 3 dz. I'm not going to even bother to look at the table. I'm going to look at the integral of the square root of z squared plus 3 times z dz, because this is really a simple substitution. We let u equal z squared plus 3, and therefore du equals 2z dz, and z dz equals 1/2 du. Okay? So I1 after the substitution will be equals to 1/2 the integral of the square root of u du. Z dz is 1/2 du, and then the integral of u. Of course, this is u to the 1/2, so solve it, and you have 1/2 times the antiderivative of the square root of u is 2/3 u to the 3/2. So we have 2/3 times u to the 3/2 plus, let's call it C1, or 1/3, and u, remember, is what? U is the square root of, u is the z squared plus 3, right? So it will be z squared plus 3 raised to the 3/2 plus some constant C1. So this is I1. We didn't use the table yet, but we'll have to use it now. For I2, we have the integral of the square root of z squared plus 3 dz. So here I'm asking you to look for a suitable formula. And that will be found in the group of radicals. '21, the first one, I believe, isn't it? So in this group, let's write it. Okay, the integral of the square root of u squared, sorry, is that a squared plus u squared, du equals 2. U over 2 times the integral, times the radical, and then plus a squared over 2 times the natural log, and here comes only expression that they're all positive, so you have u plus, is that u or a? U plus the radical plus c. Okay. So we're going to adjust. Our adjustment is this: a squared equal 3, of course u equals z, so we'll use this a as the square root of 3. So I2, based on this, equals to what? U is z, so we are looking at z over 2 times the radical plus a squared is 3, so 3/2 the natural log of z plus the radical plus the square root of z squared plus 3. plus C2. Now we need to put together I1 minus I2, and that will take place on the next page. Let me split the image. Like so. So I equal I1 minus I2. I1, just to remind you, was 1/3 Z, 1/3 the quantity Z squared plus 3 to the 3/2. Anything else? Yeah, plus C1, so we'll worry about it later. And then now we need to subtract the I2. So I2, we need to subtract Z over 2 times the radical. And then we need to subtract the natural log. So let me bring back the whole page. Like so. So let's subtract and this was, let's see, 3/2 natural log of Z plus the square root of Z squared plus 3, and then we have C. And the next thing to do is to replace Z squared. So here, let's recall where we started. That was a long time ago. So recall Z squared plus 3 was really X plus 1 squared plus 3. And this was, before we completed the square, it was simply the radicand we started with. X squared plus 2x plus 4. So whenever we see Z squared plus 3, we're going to replace it with X squared plus 2x plus 4. And whenever we see Z, we're going to replace it with X plus 1. So the integral now, we are ready to write the final answer, will be 1/3 in Z squared plus 3. So we have X squared plus 2x plus 4 raised to the power of 3/2, okay, plus or minus Z, which is X plus 1 over 2 times the square root of X squared plus 2x plus 4 plus dot 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 and dot 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 here minus the last term, which is 3 over 2, the natural log of Z, which is X plus 1, plus the square root of X squared plus 2x plus 4 plus C, where C is C1 plus C2. So this is the answer. Now, this is something. Imagine to solve this without the table. You can do each integral I1 and I2 without the table. As a matter of fact, I1, we didn't use the table. We used it only for I2, but we can do it without needing the need of a table. But it definitely saves us time. The other thing is, I mentioned that, but we talked about it on Tuesday. You don't have to apply the absolute value automatically. You need to look and see that all the terms inside the argument of the natural log, x plus 1 plus the square root and so on, they're all positive, so it's enough to put the regular parentheses. Okay? Now, of course, now somebody will ask you, if in the test I put absolute value, will I be penalized? Well, no. In this case, I won't take off points for using the absolute value. I will if the reverse is correct, though. If the expression, the argument can be negative and you don't put the absolute value, you lose. And that, I believe, the same answer I provided last time I was asked this question.